Okay, chem students, time for a little YouTube video on cyclohexane conformations. We'll look at chairs and boats, axial and equatorial positions, K equilibrium, and calculating delta H from the conformational energies. We're just going to mainly look at cyclohexane. That's the most important ring, not look at the other rings. And for cyclohexanes, the most comfortable conformation is a chair conformation. So I have actually drawn here a chair that as we are going to use, and we'll fill in all these positions. But I just put over here sort of like a little lounge chair to give you the idea of why they call it a chair. The good thing about cyclohexane chair conformations is they're staggered everywhere around. So if I look at any two positions, say like these two, this is up and it's in between the two groups in the front. This is down and it's in between the two groups in the back. It has almost zero strain energy because of its comfortable position. Very closely related to a chain where everything is anti down the line. So if I had two carbons that were connected in a chain and the carbons attached to them, okay, were anti, that would be the most stable conformation. And that's sort of what a chair looks like in a cyclohexane. Okay. Now in a cyclohexane there's a lot of perspectives we could take. I've made one chair and I've numbered it a certain way, putting number 1 on the left, most position, and then I numbered towards the front too, and all the way around, 3, 4, 5. Somehow 1 got in there. But anyway, we could cite down any two parallel bonds when we're going to make Newman projections. And so I have here, we're citing down 2 towards 3 and 6 towards 5. Okay, 2, 3, 6, 5. But you could turn around and come back the other way, 5 towards 6, 3 towards 2. So that would be two different possibilities. But we also have parallel lines and these positions here. Okay, 1 towards 6 and 3 towards 4 right here, or reverse that. And we also have two more parallel lines right here. So we could do 2 towards 1 and 4 towards 5. Okay, here, or reverse that. And usually we take whatever is the most convenient and gives us the most information about the substituents that are going to be on the ring. I always have you start with the first substituent at 1 and then number towards the front. And so your second substituent will depend on the name. 1, 2, 1, 3, 1, 4. And then you have to go by cis and trans also. So if we just pick these two parallel bonds to look at, we can think about what a Newman projection might appear as. And I usually draw arrows pointing to the first one towards the back one for myself. You don't have to do this, but I find that it helps me. And so since I'm looking at two of them, I have two eyeballs here. And in my mind, I can see this fairly clearly that left is in the back and right is in the front as I look at this. And so when I look at, say, the left guy, I'm going to see there's an axial position that goes up here, okay, on the front carbon, and that'll be here that we're looking at, okay, and so over here as well. So this is just these parallel lines help us draw Newman projections. Remember, the front guy is a dot, and the back carbon is a circle. Front carbon is a dot, and the back carbon is a circle on the right. All right. Now, as far as drawing the chair, let's go back just a moment. We're going to look on the left side here. We see the axial is up. So that'll be our first Newman projection. So we're going to start right here. The dot is the front carbon and the axial is up. Now, if you knew everything that was coming, you could draw the entire structure from that one bond. But let's just take a look. Let's go back. I see there's an H off to the left, and then the ring is off to the right towards the bottom. Okay? So you can see to the left and to the right, I'm basically dividing up the plane of the page into 3 equal wedges, but remember they're tilted towards you, so the bond angles are actually 109. But on the left we said there was going to be a hydrogen. On the right there's a ring. Now since this is cyclohexane, we're going to split everything in the back because it's all staggered. That's why cyclohexane is so stable. So I just draw those in between. And now we have to put the other side of the ring over here, so let's go back. The other side of the ring we're looking at with our right eye. So we're looking at the dot in the front. Notice axial goes up. Okay, so we draw a dot and a ring. The dot in the front has to connect to the dot in the front on the other Newman projection. and the line in the circle connects to the line, goes down to the circle, because that's in the back. Once I draw this line, actually I'm going to divide this up into 3 equal wedges, and then I'll come in between with the staggered positions, and that'll give me all the positions that I need to fill in according to the name. Okay? So this is going to be fill in the blank according to our nomenclature. There's a couple positions you might want to take a look. If I have something here, I'm actually gauche with the ring. So remember back to our chain conformations that we talked about already. This is a gauche interaction, and this is a gauche interaction, and this is a gauche interaction, and this is a gauche interaction. Okay, it depends what's there. If they're hydrogens, we don't count those. We don't put anything special in there. Okay, so if I fill in according to cyclohexane, I'm going to have hydrogens all the way around at every single position. All right, and then in the middle we have CH2s connecting over to the other side. So we don't usually write those. You just usually write CH2 if you put it in. I did put the axial position in here up and the axial position here down, just to emphasize that we have 3 axial positions on the top and 3 axial positions on the bottom. We'll talk about that a little bit more as we continue. Now the reason we call them axial positions is because if we went right through the middle of the ring with an axis, there's a C3 symmetry. So if I look over here, I have an H up, but if I rotated this H over there, everything would rotate with it, and I could not tell the difference. It would look the same. And if I rotated this H over, it would also look the same. We couldn't tell the difference. And so they call this a C3, three-way axis of symmetry, which is not something we have to be concerned with, but that's where our axial term is going to come from. Now if you look, you'll see that there's 3 axials on the top, as I just mentioned, and 3 axials on the bottom. They all point straight down, and all of these lines are parallel to each other. Okay, and you'll notice it skips. I go down, and then I'm up, and then I'm down, and then I'm up, and then I'm down, and then I'm up. So all these axial positions will alternate as we go around the ring. 3 of them down and 3 of them up. If we look at the other positions around the outside, we call these equatorial, like the equator of the Earth, going around the center of the Earth. And these are also going to alternate down and up. Now what I did was I marked these with a circle if they're up, top side of the ring, and I marked them with an asterisk if they're on the bottom side of the ring. It's hard to tell on an equatorial position because they kind of look all the same. They're just pointing off to the side. But if you look carefully, you'll see that, say in this position right here, there's an axial that's up, and this is down. Over here, the equatorial is up, and the axial is down. So remember, they alternate. So this is up, and this is down. This is up, and this is down. This is up, and this is down. And they will be the opposite of whatever the axial positions are over here. Okay, the ring's real helpful because the ring always is pointing to the axial position, up or down. Okay. Now as far as drawing the chair, there's a couple ways you could do it. I suggest you could draw 2 parallel lines, but have one about halfway down the middle of the other one. Okay, and you're going to make a V that's going to connect to these guys. It'll either be a tilted upright V or a tilted upside down V. You don't want them right on top of each other because you're going to draw some axials up there, and you don't want those to be superimposed so that you can't see what's going on. So notice how I did that. And then over here I'm going to draw a V to connect the ends. This one's a slightly upside down V. And then over here I'll draw another one. This is slightly right side up. And so there's our little chair. It takes a little practice, but easily you can do this. You know, practice 10 times and get it pretty well. So same thing here, because we're going to have to draw another conformation that's pointing the other way. So notice how I have this line here, and then I come about halfway and draw a parallel line to that. And then I'm going to connect these ends with V's. So this is an upright V, slightly tilted, and this is an upside down, slightly tilted V. And these 2 guys are going to be flipping back and forth, very fast, tens of thousands of times per second. Okay, and you'll see they have the zigzag shape around, just like a chain would have. So up, down, up. That'll help us draw the rest of the groups. Okay, so here's a typical chain. Chains like to be anti, that's the best, but remember they can rotate very quickly, so they'll have gauche and even eclipsing possibilities. but the anti shape is the most favored. Now another way is you could start with the V's. So here I started with the V slightly tilted to the right, and you don't want to put them right on top of each other. Again, leave yourself a little difference in the ends here. And then you're going to come down with the parallel lines, and then you're going to go back up with the opposite V. If you started with the V pointing down, again, have the ends off a little bit, parallel lines, and then draw the whatever a V is opposite to the first one. That gives us the same shape. It's just whatever works best for you. Okay? And again, the zigzag shape is what we're looking for. Now, as far as putting those axial positions in, the ring is real friendly to us. If we have our chair right here, chair conformation, the ring's pointing up, and the ring's pointing up, and the ring's pointing up. And you can see here why we want them slightly off center. Because if I had them right on top of each other, this line would be on top of that, and we really couldn't tell what's going on there. And then over here, we're going to come with the down, where the ring's pointing down, so we're going to point axial down, axial down, axial down. Now another thing to note is that this guy right here, I want it to be big enough so that it doesn't end in the middle of the ring, because I want to write whatever substituent is up here out of the ring. And on this one right here, notice it's in the back, so I go down and I make a little break in the line, and then I come out of the ring so I don't draw it in the middle of the ring. Okay, so that's kind of a subtle little detail, but it'll make your chairs much more understandable. Okay, and so down here we did the opposite. The axial's up, 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 and the axial's down, down, down. Leave a little break, make it go out of the ring, make this one go up above the ring with a little break in the back. Okay, so what we need to do now is put on the equatorial positions. So the equatorials are a little harder to draw, but we have a little bit of help from the ring in that they're all parallel bonds. So remember, the ring had two parallel bonds here, and the equatorial positions off to the sides of those are also parallel. So this is kind of going down like this, and this will go down at the same angle. If I come from this point of view, this is sort of going up. This will come up at the same angle. Okay, so those are equatorial. Or if I'm looking in and out here, remember we have two parallel bonds here. So I'm going to have a parallel bond in the front coming out at us, and I'll have a parallel bond in the back going away from us. We'll convert those into wedges and dashes. And then if I look at these two bonds that are parallel in the ring, also equatorial outside, be coming towards us and going back away from us. These are all parallel bonds and will help you draw a correct ring if you can recognize that. So here's the actual ring that we want. I don't draw wedges and dashes in the ring itself, but I do put them on the groups coming out at us, so those would be equatorial out or away from us, equatorial away. And then that gives us our 3D perspective of the ring. Okay, so this would be one conformation, and this would be the other conformation. You'll see that this carbon here is flipped down over here, because we're going to have to draw two different chair conformations. Now we want to put in everything, and so now we put in all the axials and equatorials. It's going to look something like this. And if I flip this down, notice the equatorial here is going to flip down to be axial on the bottom, whereas it's equatorial on the bottom here. So we have to draw these two because they're flipping back and forth and back and forth, tens of thousands of times per second. Okay, and so it's fill in the blank. Now I'm only going to give you two groups. You'll start your first group over here on the left carbon, and that'll be this carbon right here. And then we number towards the front, 2, 3, 4, 2, 3, 4. And then I'll give you some other group that'll either be at 2, 3, or 4, and it will either be cis or trans. Just remember, cis and trans corresponds to cis is same side of the ring, trans is opposite side of the ring. It does not tell you anything about axial and equatorial. If two groups are equatorial, say like this group right here and this group right here, they could be trans. This is on the top, this is on the bottom. Or it could be equatorial here and equatorial at 3, and those would be cis, because this is on the top and this is on the top. So cis and trans refer to same side or opposite side. Now, the way that two chairs get back and forth is by a boat. We're going to simplify this a little bit and just look at the boat conformation. And in the boat, if I tip, say, this end up, then these two lines will be parallel. I will only have two parallel lines now. Okay, and so I tried to draw a little boat over here to give you that idea of what a boat might look like. Now, if we use our eyes and look down these parallel bonds, the carbon in the front is the dot, so this would be our right eye, this would be our left eye. Carbon in the front is the dot, and then notice we go up to the left and up to the right, right here. Okay, and then we go straight down for axial. Now, what you're going to see is that the back carbon is exactly the same, so it's also going to be up and to the right here. They're going to be superimposed. This is going to be eclipsed. And that's an important reason why the boat is higher energy. Okay? Remember back to our chain conformations, we said a hydrogen eclipsing a hydrogen was worth 1.0. And this is 1.0. And we said that a carbon eclipsing a carbon, a methyl at the time, we said is about 2.5. And if you look over to the other side, we also have a hydrogen eclipsing and a hydrogen eclipsing. If we added all those up, that would be about 6.5. And it turns out that's very close to what the energy of a boat is. Okay, so we have 1, 2, 2.5 would make that 4.5, and on the other side, 2 more, that's 6.5. Now it's more complicated. We're not going to worry about it. I'm just going to show you, then we'll just go with the boat. But this doesn't immediately flip to the boat. It usually flips to what they call a half chair. The problem with a half chair is everything's eclipsed around the outside. Plus there's angle strain of buckling these bonds in. And that raises up the energy pretty high, 11 kcal. And so what this thing will do is it'll try to twist this to this up to a boat, but it doesn't want to keep these guys parallel because of all the eclipsing interactions. So it does what they call a twist boat. And then we get to the boat, that'll go back up because it's torsional strain, it's eclipsing interactions. And then it could twist the other way if it wanted to, or it could go to a half chair on the other side and then back down. So what we're going to do is we're going to eliminate all these things except for the boat. Right? So our flip-flop is going to look like this: chair 1, and then say we flip this guy up here, and then we flip the other side down here. So all of the axials will change to equatorials over here, and all the equatorials here will change to axials over here. But we'll just do it through a single boat, which is about 6.4 kcal higher. Okay. So now if we try and do Newman projections of these, we've already done Newman projections, say from the left side, and so I'm just drawing that right here. Notice if you're looking with your left eye here, it's going down, okay, right here, and then it's going to go back up. So this guy in the middle is going to be down. In the back side of the Newman projection, this will be up. That'll be this guy right here. Okay, and I drew in the axials and equatorials with different symbols so that you can see that the circle on the top here is axial, but becomes equatorial over here. The circle on the bottom here, which is axial, it's going to come up. It's going to be equatorial over here. And just the opposite for the squares. Okay, so hopefully you can see that. We're going through the boat. The boat has another little problem here besides these eclipsing interactions on the side. These two groups kind of tilt into the middle and bump into each other, and this is called van der Waals strain. Some people in a cyclohexane call this flagpole interactions. We're not going to emphasize this, but just pointing that out. Another reason for the strain. Okay, so if we use Newman projections here, it would look like this. Newman projections from the boat point of view is going to have both of those CH2s in the middle going up and eclipsing each other. And then if we flip this down, this will be down in the back because we're looking from the left side, and it'll be up in the front. So notice an important change in the Newman projection is that the front part here, CH2 is down, but if I come over here, the front part, the CH2 is up. So that's a little change. Now everything's going to change, so if you have some groups on here, some substituents that are either equatorial or axial, they will change when they go over here to be the opposite of that. And that'll be important when you're calculating your energies of the different chair conformations. Okay, so here's a Newman projection. This time I added in that axial in the back and added in the axial in the front, just so you can see there's 3 interactions of axial positions here, because we call that one 3-diaxial interaction, and that's true up here too. There's 3 axials that are kind of bumping into each other. Now we could calculate an energy for these guys from our little equation that we used back in chapter 5. So if we want to calculate the K equilibrium, say for a boat and a chair, we would need to know the energies. And we just said the boat is 6.4 kcal per mole higher. So we're going to make those little calories, call it 6,400 little calories. And down here, we're just going to use these numbers, 2.3, the energy constant, 2 calories per mole per degree Kelvin. And we'll assume we're about 300 degrees Kelvin. And I said you could use 1,400 calories here, little calories per mole. So we would have 6,400 over that, and that would come out 10 to the minus 4.6. So you can see this is a pretty small number. 10 to the minus 4 would be 1 out of 10,000. 10 to the minus 5 would be 1 out of 100,000. We're someplace in between. Okay, so we have this equals 2.1 times 10 to the minus 5. Okay, if we do that as a percent of the different ones, it would be a very tiny percent. Almost all chair, remember there's 2 chairs, so it's split 50-50. But that would be like 1 out of 50,000 is the boat. So it's only 1 out of 50,000, but remember, as they flop back and forth tens of thousands of times per second, it has to go up to that boat. So even though it's a tiny amount, it's going back and forth really quickly. If we look at the 2 chairs, it's even easier because the 2 chairs are equal in energy. There is no difference, so delta H is 0. 10 to the 0 is 10 to the 0, it's 1. Okay, so we have a 50-50 ratio of these 2 guys if everything is hydrogen. Okay, well, I'm not going to give you everything hydrogen. We're going to look at substituents. So let's go ahead and put a substituent on. So I made this a different color here so that you can see it. I'm going to give you a table of substituents. You don't really care what it is. You just want to know what is the axial energy. Okay, so here I started off with the equatorial position. And then if I flip this position down, that would become an axial position. And we're going to have a problem bumping into these other axial positions over here on the bottom, that 1,3 diaxial interaction. Okay, now, is this the only place it could be? No. I could flip this whole ring over, turn it upside down, and now I would have R on the top. It's still going to be equatorial. It doesn't change the energy of this guy. If I flip it up and this guy down, I'm still going to have an axial R. It's going to cost me the same amount of energy interacting with these other axial positions on the top. Okay, so if we try to draw the Newman projection of that, let's say we start off with R on the left here, equatorial. And remember, I always start at 1 and count 2 towards the front, 3, 4, go around. We only have 1 substituent right now, but the 2 parallel bonds would be 1 towards 6 and 3 towards 4. Okay, so if I look at 1, I see the hydrogen is axial up and R is off to the side. Okay, and then if I continue around with the Newman projections, I can see how does R compare to the rest of the ring. And what I see is that in the back, the 5-6 bond right here, R is anti, and that's good because R is big, and we want the big groups away from each other as far as they can get. So this is just like having a CH2 on the back on a circle guy, and it's anti. That's good. If I look over on the other side, it's also anti, but harder to see, okay, because I don't have the circle there. But it's also anti. Now, if I flipped this guy down, R goes to axial, and if I look at this side here, 1 towards 6, I see that R is down. Well, now when I look at the back of the ring, I have the big group, which is gauche, to the ring right here, and that's going to cost us a little energy, the Gauss energy. If this was just a methyl, we would say that's about 0.8. But if I look over on the other side, which I cannot see in the Newman projection, at least with this perspective, it's also going to be gauche, and that'll cost us about 0.8. So the combination of those two, we're thinking maybe it's going to be around 1.6 or so. We'll take a look in just a minute. Now here I'm trying to look from the back. So I'm looking 1 towards 2. I'm not going to have you do that because that's harder to do. But hopefully you can try and see what's going on. I see R is down, axial. And then if I look to the right, okay, I'm going to 2. So I would see there's a hydrogen there. Okay, so hydrogen is up here. And then when I look at the back, axial hydrogen will be up. And the equatorial hydrogen will be to the side. Okay. And so R, I can see it's going to be gauche with the ring at C3, right here, okay, because I'm coming from the back. R and C3 will be gauche. If I try to look at it from the front, I'm trying to show the other Gaussian interaction. I'm looking at 1 towards 6. Okay, so the dot is 1, R is down, and then off to the side here I have my ring. And in the back I'll be going down to have the ring, and if I look at R with that part with C5, that's a Gaussian interaction. So Gauss is here and Gauss is here. That's like a double Gauss. When they talk about rings, they don't say it's a double Gauss. They say R is in the axial position, and they call this axial strain. But I'm just showing you where it's coming from. It's coming from two Gauss interactions. Okay, so if we had a methyl-methyl, we said in the previous chapter, the chain conformations, that's about 0.8. And so if we have two of those, that would be 1.6. And what they actually report for an axial methyl is 1.7. Okay, so it's a little bit off, but pretty doggone close. All right. So we will call this axial strain, a strain. And if this is 1.7, then we can calculate the energy for that, just as we did before. So in this case, we're going uphill in energy. That would be a positive 1.7. But remember, it's 10 to the minus delta G. So overall, this is going to be a negative exponent because we're going uphill in energy. That would be 10 to the minus 1.2. So you can see, pretty small number. If you put that in your calculator and figure out 10 to the minus 1.2, you'll see it's 0.058. So that turns out to be a ratio of 1 to 17. If you put 0.058 and push the 1 over button on your calculator, you'll see that that's 17. That's going to be the number on the bottom here. If we figure that out as a percent, so I'd have 1 out of 18, that would be 6%. And that means the rest of it is 94%. And so if we have this methyl on here, we're looking at 94% equatorial and 6% axial. All right? So that's just one substituent, and I could put all kinds of substituents there with as long as I give you their energy. So here's a whole bunch of energies. Okay? There's even more energies, but I got this out of a book. So we have lots of different energy values. Okay, I'm kind of focusing here just on the carbon ones. So I have an H, which is our reference point. That's going to be 0. But then I could put a methyl. We just saw that one. That's 1.7. And then we could put an ethyl on. That's a little bit bigger, but not much in terms of size because we can rotate the little part into the middle of the ring. And then I could put an isopropyl on. That's a little bit bigger. And a T-butyl is really big. Okay, it's so big that we just kind of estimate what the energy is. Sometimes you see energies like 5.5, but I'll just say it's over 5. And there's all kinds of other substituents I could use, say, on the midterm. And whatever I use, I will give you that value. You don't have to memorize these or write them down. I will tell you what it is. But let's see how we use them. Okay, so first off, let's just go with the carbon ones, methyl, ethyl, isopropyl, and T-butyl. And it's pretty clear what's going on here when we do this. Okay, so we know that axial's higher energy because we're pushing it into the middle of the ring, bumping into these other 1,3 diaxial positions. This is anti to the ring. It's as far away from the ring as it can get, and that's the best. So this is always the lower energy. So if we're going axial, we're going to go uphill. Now we said for the methyl, it's 1.7. Okay, and then for the ethyl, we're going to go up 1.8. which is pretty doggone close. And then for the isopropyl, it's still pretty close, 2.1, because there's still a hydrogen here that we can point into the middle of the ring. But when we hit the T-butyl, we're in trouble. Because when I go to T-butyl, every position here is a methyl, and I'm going to have to point one of these into the middle of the ring. Okay, and so it's going to be real high. Let's take a look. So here's our equatorial group, and if these are all hydrogens, it's a pretty small group, just a methyl. But anyway, it's anti, so it doesn't even affect the ring. But if I tilt this guy up, now I'm pointing something into the middle of the ring. It's bumping into these other 1, 3, 1, 2, 3, 1, 3 diaxial positions. But if this is a hydrogen, it's not good, but it's at least it's a hydrogen. Now, as I go to an ethyl, okay, 2 of the positions are hydrogen and 1 is a methyl. So as this thing is rotating around, usually the hydrogen's going to poke into the middle. It's going to look sort of like a methyl. But if I have a methyl here, sometimes it will come into the middle, and that will bump up the energy a little bit. And you can see it is a little bit bigger, 1.8. If I have an isopropyl, then 2 of the R groups will be methyls, and 1 will be a hydrogen. So still it has a hydrogen that it can point into the middle, but 2 out of the 3 choices are methyls, and so they will come into the middle a little more often. That's going to raise the energy a bit. Okay, so now it's 2.1. And if I put a T-butyl, this is never going to be good. If I put a T-butyl, I'm always going to have a methyl in the middle, and if you look where that hydrogen is on that methyl, it's right on top of these axial methyls. And so the repulsion energy of the electron clouds is very large. Okay, so we say it's over 5. Now if you do your little K calculation for these different energies, I came up with pretty much 5% for methyl and ethyl, 3% axial for the isopropyl, and 0.02% for the T-butyl. So the T-butyl is almost 100% in the equatorial form. Right? Now if we put a second substituent on, oh my goodness, this gets a lot more difficult, because I could put that second substituent at the first position or the second position. But if I put it at the second position, it could be on the same side, cis, or opposite side, trans. Or I could put it at the third position, same side, cis, or opposite side, trans. Or I could put it at the fourth position, same side, cis, or opposite side, trans. So that means with that second group we have 7 possibilities. So you think that looks bad. That's not all. Remember, each cyclohexane has 2 different chairs. So R1 could be equatorial, or we could rotate, say down here, R1 would be axial. And R2 has the same possibilities. It could be axial or equatorial. Okay? So another possibility is the 2 R's could be the same, or the 2 R's could be different. So if the 2 R's are different, then every one of these, all these different chair conformations are going to be different. Okay? So what I suggest you do, this is my strategy, and hopefully it works for you, but if not, you can develop your own strategy. I draw the cyclohexane ring framework as a bond line formula, as we did at the start. I add in the equatorial and axial positions, okay, according to our little rules that we did. Axial points up where the ring points up. Okay, and then equatorials around to the side with some parallel bonds in the ring that you can use. Remember, they will alternate on top and bottom, both of them. Okay, then we want to add in the necessary substituents. Well, I'm going to give you something with 2 substituents. So that'll be 2 things that you got to put on according to the name. Everything else will be hydrogen. Okay, so those would be easy to fill in, but the 2 substituents have to be in just the right spot. Okay, I'm going to have you draw C1, according to the name, on the leftmost carbon, and then number towards the front for C2, 3, 4, and so forth. Okay, so I do that for my own benefit, so when I'm grading your exams, I don't have to try and figure out everybody's strategy. And then you're going to draw the other conformation, so you'll flip one side up and one side down, and hopefully you can draw those chairs just as easily as the first one. But remember, wherever the substituents are, if they're axial, they will become equatorial, and if they're equatorial, they will become axial. So make sure you remember that. Okay, now there's one place where you have to be a little bit careful, and that is if I gave you a name that is 1, 2. If I gave you a name that's 1, 2, then the 2 substituents on the side of each other could be gauche. So that's an extra gauche you would have to add in. And so you have to recognize that. It's a little hard to see because remember they're off to the side. So just be careful on that. We'll look at an example in just a moment here. Okay, and if they're only methyls, we'll just call it 0.8. Or I might tell you that the gauche interaction has a certain value, and then you'll use that value according to what I tell you. But if I don't say anything, you can just assume it's 0.8. So what you'll see is that each conformation will have an energy. And then you'll calculate that difference in energy, and that's the value you'll put into the little equation that we use to calculate the ratio between the 2 conformations based on that. Okay, so it's really delta G, but we approximate delta G as delta H. So let's take a look at an example. I'm going to start off with 2 substituents that are the same. They're both methyls. Okay, so first I draw a cyclohexane framework. I did here, according this way. And then since the name says 1, 2, I put in like the positions there, equatorial and axial. Axial's down, axial's up because the ring's pointing up. Equatorial's off to the side, parallel to these bonds. And then I got to fill in the name, the substituents according to the name. So I'm saying it's trans 1,2-dimethyl. So I'm going to start with the methyl in the equatorial position, so H will be down. And since I say trans, I drew the methyl on the top. I'm going to have to draw the methyl on the bottom over here. Now, it might look like, since this is equatorial, I should be drawing it axial, because it sounds different. But axial is on the top here. And if it's trans, I have to draw the other methyl on the bottom, which will also be equatorial. Okay? And then I fill in the H here. Now, in the exam, I'm going to have you fill in the rest of them too, all the hydrogens. But I'm just putting these two here so we can focus on the energy of these conformations. Okay, so now what I have to do, since I've drawn this one, I have to flip this guy up and flip this guy down to draw the other chair. Now when I flip this guy up, it's going to become axial. Okay, and when I flip this guy down, it's going to become axial. So now instead of my two methyl groups being equatorial, they're both going to be axial. And remember, the axial energy is different. So over here I have to look, since I 1,2, I have to look for that possible Gauss interaction. And sure enough, there it is. These two guys are Gauss to each other. If you were to cite down, say the 2 to the 1. Okay? And over here, they are not Gauss to each other, but they are Gauss 2 times on the ring. Remember, that's the 1.7 A string. So the energy on this side will be 0.8 because of the side groups, the methyl groups. And the energy over here is an axial on the top and an axial on the bottom. Each of those is 1.7, so I have two of those, that's 3.4. So the difference in energy between these two is 3.4 minus 0.8. Okay, so that'll be 2.6. So we'll use that 2.6 kcals, we'll make it into 2,600 little calories. It's a positive energy because we're going uphill in energy, so the exponent is going to be negative. So I have 2,600 divided 1,400. 10 to the negative 1.9. It's almost like 10 to the negative 2. So it's around 1 out of 100. But you know, it's actually 1 out of 79. So that would be 1.3% where these are in the diaxial position, and 98.7% where they're both in the equatorial position. Our energy diagram would look something like this. Remember, it's uphill about 6.4 or so to the boat. And the difference is 2.6 kcals. All right, so that's the way the problem would look if they were both methyls and if they were on the 1,2 position. Now, as far as drawing the Newman projection, I would tell you in the problem, use the C2 to C1 bond and the C4 to C5 bond. So I've shown those here. Again, I use eyeballs to kind of put my mind into location and arrows pointing to the direction I want to go. But you can do it however you want. So remember, our first carbon is as a dot. So this is on the left side here. So our dot down here on the left side will have a methyl off to the side, and in the back it'll have a methyl off to the side. And then we fill in all the rest of them with hydrogens, okay, in the staggered conformation. You can see here now the Gauss interaction that we were talking about, okay, and that's going to cost us about 0.8. If I flip this down and flip this up, then the methyl in the front will be straight down, which I have here on the left, and the methyl in the back will be straight up, which I have here on the left, straight up. And then everything's staggered. Dot connects over to dot, circle connects over to circle. So you can see why you want to be able to draw these. And so now when I look at this, I can see the two methyls are anti to each other, but this one on the top here is Gauss to the ring here in the front, and this one on the back is Gauss here to the carbon in the back there. And so I can see two of them, but remember, this methyl is also Gauss over here, and this is also Gauss over here. But I only show two of them. So you would have to show those Gauss interactions, and you would have to show this Gauss interaction wherever you can see them. Okay, and so if you could do all that, then you would get this problem completely correct. Now what I did here was I used two different substituents because that's what I might do on the exam. So I'm saying R1 is not R2, and the substituents I picked would be this guy here. It's called a sulfone. You don't have to know that. I would give that to you if it was something we didn't know about. And then this group right here is a nitro. You should know that one because that's on your nomenclature list. So then I have these two groups. Well, you would have to know the energies of these, and I would tell you that. So I'm telling you the methyl sulfone has an axial energy of 2.5, and the axial nitro has an axial energy of 1.1. So in every single possible name, you're going to have, both of these groups are going to be axial at some point. So let's just go across here. Here I have 1, 4, and you can see these are trans. So I might tell you that the two substituents are trans. I drew that over here so that you could see that. Okay, so that would be here. So the axial sulfone would be plus 2.5, and the axial nitro would be 1.1, and I would add those together, and I would get 3.6 for the energy of this conformation. If I rotate to the other conformation, which looks like this, I have no energy expense. They're both anti to the ring, they're not close to each other, and so this energy would be 0. The difference between these two would be whatever the energy values were. In this case, it's 3.6 kcals. We would make that into 3,600 little calories and divide that by 1,400, and that would become the exponent. K equals 10 to the minus whatever that exponent is. Well, I didn't do all the work, but I did show you the number, the ratio, which is 1 to 370, because of this energy difference of 3.6 kcals. So it's essentially 100% the diequatorial conformation. Now, if I went to the cis, then I would have to draw one of these equatorial and the other one axial. Flipping over, I would have the first one axial and the other one equatorial. So there would be no cost for the equatorial, but now the cost is whatever the axial cost is. So remember up here, Y is nitro, that would be 1.1. And X is the methyl sulfone, and that would be 2.5. So the difference between these two would be 2.5 minus 1.1, which is 1.4. And then we could calculate it, an equilibrium constant, which I did here. And so I actually have like 7 problems here. 1, 2, 3, 4, 5, 6, 7. They all use the same numbers that I just talked about, so you could substitute those in pretty easily. The only thing you have to worry about is if they are 1, 2 down here at the end. So this one is cis 1, 2, and this one is trans 1, 2. Okay? And so in that case, you might have some gauche interactions, and on this I said count the gauche interactions as 1.0. So if we look at that, say this one right here. Okay, I have an axial Y, which is a nitro, that's 1.1, but I also have a gauche. Okay, these two are gauche, so that's going to be 2.1. On the other conformation of the cis, I have an axial X, which is 2.5, we said, but they are also still gauche. So that's going to cost us an extra 1.1. That'll be 3.6. Minus 2.1, the difference will be 1.5, and that's what you would calculate the ratio with. Notice on the trans, they're gauche when they're equatorial, but they're anti, so I don't have to worry about that gauche energy of 1.0 here. So on the 1,2 conformations, you do have to worry about the gauche. And this is 1,1, so they're not going to interfere with each other because they're on the same carbon. Okay, so here's our little K equilibrium that I use to do all these little calculations. You have the answer by the ratio that I have here. Now, the last part of this particular problem on the exam, I give you cyclohexanes with 3 methyl groups. And then I tell you the possible energies are, we already know one methyl is 1.7. But if 2 methyls were on the same side, they would really crowd each other more than 2 times 1.7 because they're so big. And so I tell you the energy when they're on the same side is 5.5. Now, there's only one possibility, but they could all 3 be on the same side, and that would be a lot of energy because they're really crowding each other, and I tell you that's 12.9. And then our gauche interaction is 0.8. So knowing these numbers right here, you could calculate the energy of every single cyclohexane here. So what I will do on the exam is I will give you one of these, and then I will give you its other conformation if it flips. So I have 5 examples here. So if I put all the methyls, 1, 3, and 5, like this, nobody's axial. Nobody's gauche. They're not next to each other, so that would be 0. If I flip to the other conformation, so flip this down and flip these up, then I'm going to get all 3 methyls on the same side, and that's going to be really high. So the difference between these two would be the most stable possibility, And the least stable possibility, that would be 12.9 for delta H. That's going to be basically nothing of this, almost 100% of this. Okay, let's come over here and take a look. So if I had this one, I would flip this up, so that would be axial, and that would be equatorial. This would become equatorial on the bottom, as it is here, axial on the bottom. And so I would have a cost here, if I have the two methyls on the same side, that's 5.5. This cost us nothing. And then here I would have equatorial all by itself. Equatorial all by itself costs us nothing, but I do have one axial. That would cost us 1.7. So the delta between these two would be 5.5 minus 1.7. You could plug that in. And over here I have basically an axial. Okay, these are both equatorial, but since it's 1, 2, I have to be careful because I do have a Gaussian interaction here, and I do have a Gaussian interaction here. So that's going to cost me 2 times 0.8. So altogether that's going to be 3.3. Okay, 1.6 and 1.7. And then if I look at this, I have an axial and an axial, but on opposite sides. This one doesn't oh, this one does. There's a Gauss right here. So I'm going to have a axial, and one Gauss. That'll be 4.2. So the difference between these two would be 0.9. These are all equatorial. That's good, except it's 1, 2, and 3. So there's a Gauss here, and there's a Gauss here. I'm going to have 2 Gauss. That's going to be 1.6. If I rotate this up and rotate these down, everybody goes axial. So I'm going to have a bad 2 methyls on the same side here. It costs me 5.5. But the other axial is on the bottom side, opposite face, 1.7. Altogether, that's going to be 7.2. So the delta would be 7.2 minus 1.6. Here I have everything equatorial again. That's good. This guy's far away, so it's not 1, 2. That's cost us nothing. But I do have 1 Gauss right here. That costs us 0.8. If I flip to the other conformation, I have an axial up, 1.7. Then I have 2 axials down. That's going to cost 5.5. Again, that would be 7.2. And so you figure out the delta. So you can see each situation here is a little bit different. It's not real hard to figure it out. And hopefully you'll be able to do that. Okay, so I think that